Hello dear student, as we have completed our discussion on the chapter diffraction, let's solve some problems on the same chapter. This is part 1 of problems. In this chapter you have already learned about the phenomenon of diffraction, classification of diffraction as Fresnel and Fraunhofer. You have learned the Fresnel theory of approximate rectilinear propagation of light. You have seen different diffraction patterns such as Fresnel diffraction at straight edge and circular edge. You have seen Fraunhofer diffraction at a single slit, Fraunhofer diffraction at two slits as well as many slits. You have seen how plane transmission through grating occurs and also how to determine the wavelength of the light using grating. So diffraction is a phenomenon which is defined as bending of light around the corners of an object so that we can see some kind of a pattern and interleaved dark and white bands towards the geometrical shadow of that aperture or the obstacle. This phenomenon is seen when the aperture is very small, that is when the aperture is compatible with the wavelength of the light. There are two types of diffraction, the Fresnel diffraction and Fraunhofer diffraction. In Fresnel diffraction, the source, the obstacle as well as the screen are at finite distances, so that the wavefronts we are talking here are either spherical or cylindrical. In Fraunhofer diffraction, the source, the obstacle as well as the screen are at infinite distances, so that the wavefronts we are talking here are plane wavefronts. Either if we do not have an infinite distance, we use some convex lenses to make them appear as parallel lights. So the first type of diffraction pattern we have discussed is the Fresnel diffraction at a circular aperture. So this is the pattern of the Fresnel diffraction at a circular aperture. For this type of diffraction, you will have a source at a finite distance, and the distance from the source to the circular aperture is A, and the distance from the circular aperture to the center of the screen is B. At the screen you will see some pattern like this, that you will have airy disc and rings of alternating dark and light bands. And if you move this screen from infinity towards this point, at the infinity you will only see a light, a complete bright light here. As you move towards the screen or towards the aperture, you will see alternating light, dark bands appearing in the screen. And these alternating dark bands are due to the superposition of the half-wave plates. If two half-wave plates are superpositioned, that is when n is even, you will have a dark band at the center. If the n is odd, you will have a bright band at the center. So the center point P alternates dark and bright as you move at the screen from infinity towards the aperture. And the number of rings inside this area keeps on increasing as you move the screen from infinity towards the circular aperture. Let's solve our first problem. A point source of wavelength lambda is equal to 550 nanometer is placed 2 meter away along a circular aperture of radius 2 millimeters. On the other hand, a screen is moved along the axis from infinity to closer distances. Calculate the first three positions where the minima are observed. So we are asked to calculate when a screen is moved from infinity towards an circular aperture. We are asked to find the position when we will see three dark bands. as I've already discussed, at infinity you will only see a white spot of light. You will see dark bands when it is moved towards the circular aperture. So what are the points at which, geometrical points at which you will see these dark bands? This is what you have to find. So we already have an equation, that is 1 by A plus 1 by B is equal to n lambda by r squared. Here A is the distance of source to the aperture and it is given as 2 meter. B is what we have to find, and n. We are said we need to find the minima. So minima are observed when n is even. We have to find the first 3 positions. So the first 3 positions are 4, 6 and 8. We are eliminating 2 because when we put 2, the equation B become negative. So we are eliminating 2 and the possible answers are 4, 6 and 8. So let's write an equation for n from this equation. So n is equal to r squared by lambda, and also r squared. Our r is the radius of the aperture and it is given as 2 millimeter. So 2 into 10 to the power negative 3 meter. So n is equal to r squared by lambda 1 by A plus 1 by B. So here r squared is 2 into 10 to the power negative 3 the whole squared divided by lambda, which is given as 550 nanometer, that is 10 to the power negative 9, into 1 by A. A is given as 2 meter plus 1 by B. We need to find B. This is a common equation. Let's start. At n is equal to 4, you will see the first dark circle. So let's put 4 is equal to 2 into 10 to the power negative 3 the whole squared divided by 550 into 10 to the power negative 9 into 1 by 2 plus 1 by B. When you solve for B, B will be equal to 19.98 meter. That is, when you move this screen from infinity towards the aperture at a distance 19.98 meters from the center of the aperture, you will see the first dark band. Continuing the same arguments, for n is equal to 6, you will find B is equal to 3.076 meter, and for n is equal to 8, B will be equal to 1.664 meters. So at 3.076 as well as at 1.66, you will see additions of other 2 dark bands into the diffraction patterns. Let's discuss the next question. A parallel beam of wavelength 600 nanometer falls normally on a circular aperture of radius 0.9 millimeter. At what distance along the axis will the first minimum intensity be observed? So the question is the distance at which we need to, so you have a screen here, you have a source here, and the question is at what distance you should place this screen such that you will see the first maximum. So the first maximum we know maximums are observed when n is odd. So the first maximum is observed when n is equal to 1. First maxima, we have n is equal to 1. Again, what are the information other than that? We have a wavelength which is 600 nanometer. The radius r is 0.9 millimeter. We need to find B. Now what about A? The source, A is the distance of the source and the aperture. We do not have any explicit information about A, but it is given the planes or the beams we are dealing with are parallel beams. If the beams we are dealing with are parallel beams, it seems that we do not have circular wavefronts or cylindrical wavefronts here. The wavefronts have flattened enough so that we are dealing with plane wavefronts. If we are dealing with plane wavefronts, which indicate that our source is not at a finite distance but is at an infinite distance, then only we can have parallel beams near the aperture. So let's solve the problem. What are our equation? We have the equation 1 by A plus 1 by B is equal to n lambda by r squared. We have A is infinity. We need to find B. We have n is 1 because they are asking for first minima. We have lambda as 600 nanometer. And we have r squared, that is 0.9 millimeter. So B is equal to 0.89 10 to the power negative 6 divided by 600 into 10 to the power negative 9, and you will get B as 1.35 meter. That is, at 1.35 meter from the aperture, when you place the screen, you will get the first maximum. So we have done our discussion with Fresnel diffraction at circular edges. Let's continue our discussion with Fresnel diffraction at single edge. So at a single edge, you will be having a plane beam or an obstacle. The obstacle will be covered with an opaque something and it will be open in the other half. So at normal distances, the other half will be illuminated and the obstructed part will be dark. But when you move towards the source, you will find alternating dark and white patterns in the illuminated area, in the formerly illuminated area, and the dark area remains dark itself, but in the formerly illuminated area you will see alternating dark and white band. This is a Fresnel diffraction at a straight edge. This is how its pattern will look like. We have equations for the position of maxima and minima. The maxima are observed when we have x is equal to odd multiple of n into a plus b into b lambda divided by a, and minima are observed when we have even multiples of n multiplied by this factor a plus b into b lambda divided by a. Similar to what we have discussed, A is the distance from the source to the aperture, B is the distance from the aperture to the screen. So let's discuss the questions. The first question is, In a particular experiment, lambda is equal to 600 nanometer. The distance between the slit source and the straight edge is 6 meter, and distance between that of the eyepiece is 4 meter. Calculate the position of the first 3 maxima and their separation. So, what are the examples, the values we have got? We have got lambda, that is 600 nanometer. The distance between the source and the straight edge is 6 meter. So, A is 6 meter. And the distance between the edge and the eyepiece. The eyepiece here is a screen, or anything that captures the image is screen. So here B, that is a distance to the screen, is 4 meter. We are asked to calculate the position of 3 maxima and their separation. We know maxima occurs at positions where xn is the odd multiple, that is 2n plus 1 of the factor a plus b into b lambda by a. So let us calculate this fraction first, because this is almost a constant. So let's calculate for that. So let's calculate a plus b into b lambda by a. Let's see, root over this. So root over a is 6 plus 4 into 4 divided by 6 into 600 to 10 to the power negative 9. So this is 10. This is 10 into 4, that is 40. Again you have 100 here, so it becomes 4000. You have 10 to the power negative 9 here, so all of a sudden you will have 4 into, let's see, instead of 1000 I would like to, instead of 1000 let me write it as 100 and subtract 1 from this, so it is 10 to the power negative 8. When it is come out of the root, it will become 2 into 10 into 10 to the power negative 4, which will be 2 into 10 to the power negative 3. So the value of our k is 2 into 10 to the power negative 3 meters. So we will observe these maximas when this particular number is odd. So the first maxima, when the first odd number x is equal to 1, will be observed at 2 into 10 to the power negative 3 into root over 1, which will be nothing less 2 into 10 to the power negative 3 meter. The second maxima will be observed at the odd number x3. So it is 2 into 10 to the power negative 3 into root over 3. Root 3 is about 1.732. So the answer will be 3.46 into 10 to the power negative 3 meters. The next maxima will be at 5. So the answer is 2 into 10 to the power negative 3 into root 5. And the value of root 5 is around 2.236. So the answer is 4.47 into 10 to the power negative 3 meters. So these are the positions at which you will observe the three maximas. And also you are asked to calculate their separation. So the separation between the first maxima, the first bright band, and the second bright band, that is the second maxima, is the difference between these two, and it appears to be equal to 1.46 into 10 to the power negative 3 meters, and the distance between the second maxima and the third maxima, that is the second and third white bands, it is around 1.01 into 10 to the power negative 3 meters. As you can see, the distance between them come closer and closer as the number of maxima or n increases. Next type of diffraction is Fraunhofer diffraction. So Fraunhofer diffraction is the diffraction when we are dealing with plane wavefronts, or we have source, the slit and the screen at infinite distances. So at Fraunhofer diffraction, what you see here is the Fraunhofer diffraction. You will have a central maxima and other secondary maximas towards either side of the central maxima with decreased intensity patterns. So for constructive interference, A sin theta is equal to n lambda, where A is the width of the slit. You will have one slit and the distance of the slit is A, and A sin theta is equal to n lambda for a destructive interference or the minima, and for constructive interference A sin theta will be equal to odd number of lambda by 2, that is 2n plus 1 lambda by 2, and we will get a constructive interference or the maxima. The width of the central maximum, that is this width, the width of the central maximum. Here this is the width of the central maximum. This will be 2 times the distance, this distance. So it is 2x is given by 2f lambda by A, and this is also equal to 2d lambda by A. This is the width of the central maximum. So let's discuss the question. The question is, a slit with A is illuminated by a white light. For what value of A does the first minimum for a red light of a wavelength 650 nanometer fall at an angle of diffraction theta is equal to 15 degrees. So what we need to find is for a minimum, and we need to find the value of A, that is the slit width. So we have an equation, A sin theta is equal to n lambda for a minimum. So we need to find A. We have sin lambda. The lambda here is 15 degrees is equal to, it is for the first minimum. So for the first minimum, n is equal to 1. So n equal to 1 into lambda. Here lambda is 650 nanometer, 10 to the power negative 9 meter. So A is equal to 650 into 10 to the power negative 9 divided by sine 15 degrees. Sine 15 degrees is 0.2588. So when you solve this, A will be equal to 2.51 into 10 to the power negative 6 meter, or you can write it as 2.51 micrometer. So when the slit width is 2.51 micrometer, then the red light of wavelength 650 nanometer, which is falling at a diffraction angle 15 degree, can make you find the first minimum. Second question, red light of wavelength 6500 angstrom from a distant source falls on a slit of 0.5 millimeter wide. What is the distance between the two dark bands on each side of the central bright band of the diffraction pattern observed on the screen, which is placed 1.8 meter from the slit? So let's write down the values given first. We have lambda is equal to 6500 angstrom, which is 10 to the power negative 10 meter. So we have A, which is given to be 0.5 millimeter, 10 to the power negative 3 meter. We are given the distance at which the screen is placed, that is D. D is given to be 1.8 meter. So what are we asked to find? We are asked to find the distance between the two dark bands on each side of the central white band. So when we plot our intensities, this is our central white band. So this whole thing is our central white band. This is our first dark bands on the either side. So what we are asked to find is just this distance between these 2 points. So the distance between these 2 points is nothing but our width of the central maxima. So what we are asked to find is the width of the central maxima. So to find the width of the central maxima, we already have the equation 2x, that is width of the central maxima, is equal to 2 times d lambda by a. So let's substitute 2 into d, 1.8 meter, into lambda 6500 into 10 to the power negative 10 divided by a, that is 0.5 into 10 to the power negative 3. So when you solve, you will get the central maxima as 4.68 millimeters. So the distance between the first 2 dark bands on the either side, this distance is 4.68 millimeter. Next question. A parallel beam of monochromatic light of wavelength 6000 angstrom incident normally on a narrow slit of width 0.3 millimeter. The diffraction pattern is observed on a screen. Calculate the angular separation between. The first question here is the first minima minimum and central maxima. Okay, you need to find the angular separation. So you need to find the theta. This is just the theta. So what are the values given here? You have given lambda, that is 600 angstrom. You have given the value of width, that is a is 0.3 millimeter, and you need to find the value of theta, the angular separation. theta. So what is the angular separation theta between the first minimum? Where do you observe the first minimum? This is the first minimum. And the central maximum. This is the central maximum. So the distance theta between the first minimum and the central maximum is nothing but lambda by A. You already have values 6000 into 10 to the power negative 10 divided by 0.3 into 10 to the power negative 3. So the answer you observe will be in radians. Okay. Now question number B. And the answer is 2 into 10 to the power negative 3 radians. The question B is first maxima. First maxima is nothing but the central maxima. First maxima on both sides. First maxima on both sides of the central maxima. Okay. So this is the first maxima. This is the first maxima. So we need to find the distance between the first maxima on the both sides of the central maxima. So you will observe the first minima here, the second minima, third minima over here. Again, first maxima will be observed at 3/2 lambda by A. Next maxima will be at 5/2 lambda by A at odd numbers. So the distance here it is observed at minus 3/2 lambda by A. At even positions you will observe minima, and at odd positions 3/2, 5/2 etc. you will observe these maximas. So it is 3/2 lambda minus 3/2 lambda by E to 3/2 lambda by E. So this is again minus 3/2 plus this 3/2. So the distance, this is the distance, and this distance is 3 lambda by A. 2 times 3/2 lambda by A is 3 lambda by E. So the theta is 3 times lambda by E. You have already found the value of lambda by E is 2 into 10 to the power negative 3. So 3 times is 6 into 10 to the power negative 3 radians. Okay, hope you have found it. This is the central maxima, and every maxima occurs at odd positions and every minima occurs at even positions. So let's move on to the next question. A lens whose focal length is 40 centimeter forms a Fraunhofer diffraction pattern of a slit 0.3 millimeter wide. Calculate the distance of the first dark band and the next bright band from the axis. You are asked to find the distance of the first dark band, this one, and the next bright band, this one, from the center. So when you are asked to find the distance, they actually means is the geometrical distance. So what you need to find is the x, not the theta value, the x value corresponding to these theta. So we already have the values. So we have the equation. First we need to find the first dark band. For dark band, the equation is A sin theta is equal to n lambda. This is the first dark band. For first dark band, we know that theta is lambda by d. So the angular separation or the angular distance theta is lambda by d, or lambda by a is the angular separation. It happens when n is equal to 1. So first dark band is at n equal to 1. So for n equal to 1, this equation becomes a sin theta is equal to lambda and sin theta, which is approximately equal to theta. For small angles of theta is equal to lambda by a. We have an equation for theta which can be observed from the geometry of the arrangement, that is theta is given by x by f. Therefore x is the geometrical distance. X by f is equal to lambda by a and x is equal to lambda f by a. So by substituting the values, lambda is given as 5890 angstrom, 10 to the power negative 10. F is the focal length and it is given by 40 centimeter, 10 to the power negative 2, divided by the slit width, that is 0.3 into 10 to the power negative 3. So x is 0.785 millimeter. So this is the answer for our first, that is for the first dark band. Now next we need to find the next bright band that occurs here when theta is equal to 3 by 2 lambda by a. So for the next bright band, that is not the central bright band but the first bright band after central. So here for that theta is equal to 3 by 2 lambda by a, but theta is x by f, therefore x by f is equal to 3 by 2 lambda by a, which gives us x is equal to 3 by 2 lambda f by a. You already have an equation for lambda f by a, so multiplying it with 3 by 2 will give you 1.178 millimeter. Therefore this point in x scale is 1.178 millimeter and this point, the dark point on x scale, is 0.785 millimeter. So thank you for watching the video. We will see in the next video.